morning, everyone. My name is Shafiq, or Muhammad Shafiq bin Muhammad Sulaiman, the full name. Today, I would like to share with you all about intermediate range taper optical fiber and how we can do it. Okay. These are the 7 main points of this talk, which I will briefly talk about what kind of taper we have for now, and also very briefly why we do tapering, and then I will describe about dispersion decreasing fiber, or DDF, and then about adiabatic soliton compression, and we will go about the mechanism or what we have done so far with this type of tapering, and then very briefly about wave shaper and also problems and future. So, tapering have been widely investigated over past decades, but we have short tapering and also long tapering, which are available with flame brushing and also drawing power. However, we have this huge gap between this short and long tapering, and so that's why we will try to have the intermediate tapering range. So these are some reasons why we do tapering. As the core radius decrease with the same factor of the total fiber, and so by doing tapering, we can change the effective mode of one end, and then we can improve our coupling. The other reason is mode filtering, which by doing the tapering, we will alter the normalized frequency, and then that means we will alter which mode is propagated in the fiber. By strongly tapering a fiber, we will then, when we do strong tapering, we have the core will diminish, and so we have air cladding interface, and so by altering the air surrounding like sulfur or anything, we will have highly nonlinear fiber. And lastly, adiabatic soliton compression is what we are trying to achieve in this study. Phase velocity and group velocity propagate in the fiber are influenced by optical frequency. This phenomenon is called chromatic dispersion, which is made of material dispersion and waveguide dispersion. Here is material dispersion, and down here is waveguide dispersion, and over here is chromatic dispersion, which is the total of waveguide and material dispersion. So we simulate how, by doing tapering, what changes in the fiber. So according to this eigenvalue equation, which J and K is the Bessel function for core and cladding, by doing tapering, we will change the effective magnetic index, effective refractive index, and so we'll change the waveguide dispersion, and in total we'll change the chromatic dispersion. And by having this simulation, we can see that in anomalous range of lambda, we will decrease the beta 2, and by having the beta 2 at 1550, we can see in this range of tapering, we almost have a linearly fit beta 2 function according to core radius. So with this well-defined beta 2, we can simulate how soliton propagates in a fiber. So the simplest fundamental soliton in non-loss fiber will maintain its energy, and so by having this energy, it will remain its shape and amplitude. And so by knowing this, when we alter beta 2, it will consequently result in decrease in pulse duration. So simulation of soliton in a fiber, we use a nonlinear Schrodinger equation. We alter it a little bit because we have beta 2 changes in spatial space. So we have dz from 0 to 1 as a decreasing function. And so by specifying this dz and having a hyperbolic profile, this changing in beta 2 will result in a gain as pulse propagates down the fiber. Here is some very brief condition on adiabatic soliton compression. The interesting part is we need to have soliton as at the input, and by having this, we can actually make advantage of when we use, for example, higher order soliton, where we know soliton will get, for example, pulse duration will get smaller, and so we can make use of that part and make it propagate through a tapered fiber. And here is the simulation of 300 femtosecond input soliton down through 15 meter fiber. So previously we have shown that we have a linear relation of beta 2 and core radius. With that, we can have the ratio of input beta 2 and output beta 2. With that, we can get a well-known output. However, this however in a non-loss fiber. The other thing need to note that we are propagating 300 femtosecond pulse, which if we try to propagate 10 picosecond pulse, we probably need like kilometers, but over here with 300 femtosecond, we only need 15 meters and possibly shorter. However, as we know, fiber has losses. So here is the example of pulse in a lost fiber, and here is the same pulse in a tapered fiber. So by carefully design our tapering profile, we can actually not only compensate the loss, but we also can get a gain as pulse propagate. Here is what we have currently in. So here is what we have now in lab. Over here we have both commercial measuring head and microheater, and over here we have feeding motors, and over here we have drawing motors. So fibers will start from here through here. With the equation that governs both motors are this conservation of mass equation. With this equation also, every input from the measuring head will then recalculated for error check, and then will be completed again to get our desired profile. And because we are using commercial measuring head, the frequency of measurement is quite high, and so we can minimize our error. With this kind of method also, we can get almost any profile tapering that we want. So here is some simulation of profile, the linear profile. Another advantage of using the heater is that we will have a huge reduction in temperature fluctuation and also less impurement. With that, we can, for example, use around 1000 or 1200 to get where at this temperature silica is just soft enough to be tapered. Wave shaper is another instrument that we might be used in this project, where by using wave shaper we can get filter center frequency accurately, we can set the attenuation level, we can have a desired filter shape, and also phase. Phase is probably the one that we can set up with what our project. Here is the example of our pass, our filtered pass according to the rectangular pass or sinc function. However, this comes with at least 5 dB loss. However, at this point we still don't have any laboratory result yet, but let's ponder upon future. First, for example, we can include in our experiment coatings after the measurement, and also we can accurately observe the tension in the system. We can also improve the feedback loop in order to decrease the error, and we will also like to look into chemical stripping where there is possibility of crystallization. That's all for today.